previous lecture, we've seen how contrast arises and how amplitude varies when the electron beam interacts with a specimen. We've introduced briefly what the structure factor is, and we've also connected it to diffraction. Now we'll start with the simplest imaging mode in TEM. We'll try to understand what is amplitude contrast and how do the TEM micrographs have the variations in the intensity when the electron beam is interacting with the specimen. So broadly, let us look at the various contrast mechanisms in TEM. We have mainly a broad distinction called as the amplitude contrast and the phase contrast. Let us look at amplitude contrast. So essentially, this originates from changes in the electron wave amplitude as electrons interact with the specimen. So if I say psi I is the incident wave and this has some amplitude psi naught, sin kx minus omega t, on undergoing scattering, let us say the amplitude here is psi naught prime sin kx minus omega t. This change in amplitude as a consequence of the scattering phenomenon that has happened is what is recorded in an image, and this amplitude variation can be related to the Rutherford backscattering expression, from where we related the angle of deviation of the scattered beam to the intensity of the scattered beam as well. So broadly, this can be viewed as something called as mass thickness contrast. In principle, as a function of the atomic number variation or a change in the thickness of the specimen, the intensity of the forward scattered electron in a transmission electron microscope is going to vary. So what does this mass thickness contrast tell you? Heavier atoms scatter electrons more strongly than the light atoms. So if you recollect the expression for scattering cross section as a function of angle of scatter, this is related to the atomic number, and stronger the and heavier the atomic number, stronger the scattering event. So what happens is, suppose I have a system with light elements and heavy elements, say aluminum and tungsten. Tungsten is going to deviate the electron beam stronger, or it is going to scatter is stronger, and you can always determine how much such a heavy atom is going to result in change in the amplitude of the scattered beam. Likewise, aluminum is going to scatter it slightly weaker. So also, thickness gives you a strong influence on the variation in the amplitude. Thicker regions typically tend to scatter more than thinner regions, and if you are recording a conventional bright field image, thicker and heavier regions appear darker on a bright field image. There is something else called as diffraction contrast, which is also a form of amplitude contrast. If you remember from the previous lecture, we've seen the variation in the structure factor as a function of the atomic scattering factor, and we've seen that for an amorphous material, the variation in intensity is random, whereas for a crystalline material, you had changes in peaks. And as you go farther away from the optic axis, or as the angle of scatter is increasing more and more, the amplitude also drops down. The positions of these peaks and the amplitudes we've already established are dependent on the crystallinity of the material and also the atomic number. So the intensity variation in a diffraction pattern or the diffraction contrast is caused by electrons diffracted according to crystal orientation and Bragg conditions. When you are recording bright field images, as a consequence of variations in the internal arrangement of atoms within a sample, say you have a polycrystalline material with different grains, grains oriented in different directions will give you variations in diffraction contrast as well, and you see a consequence of this in the bright field image that you record. And also there are special conditions where you can orient the specimen to get what is called as a dark field image. This is a special form of imaging that you use to actually record defects or some specific features. We will look at bright field images and how the contrast arises in a transmission electron microscope. So, in diffraction patterns, the amplitude contrast appears as differences in the spot intensity, and here is a one-dimensional variation in intensity which we've sort of seen in the previous lecture also. We will look at how the mass thickness contrast arises and how to quantify this, and we'll look at a few examples. We'll first look at only the imaging contrast variations. I'll show you some example images, and then we'll establish a sort of a protocol on how you obtain basic bright field images in the TEM. What is the sequence in which you do this? After we look at the lab demonstration of obtaining these bright field images, then we will look at some foundational concepts in diffraction again, and then look at the variations in diffraction contrast and understanding diffraction patterns in more details in the subsequent lectures. So, to quantify mass thickness contrast, simply I was mentioning to you something called as a bright field image or a dark field image. Now, if you look at just this empty screen here, the background looks bright and the features of interest start appearing darker. The text that I want to present you appears darker. Likewise, in a transmission electron microscope, when I do not have any specimen in the path of the electron beam that is hitting my detector, the entire detector is now illuminated with more or less uniform intensity and it starts appearing brighter. Now, when I insert a specimen in the path of the electron beam, what happens is, as a consequence of scattering from the specimen, you have a deviation in the path of the electron beam, and within the specimen again, if you have variations in the mass and the thickness, you will have some additional changes in the intensity of the scattered beam as well. So, broadly speaking, if I write in a bright field image the intensity variation versus the background as some function like this, delta I over I, where I is the background intensity, you can relate this as some kind of an expression like this, some exponential where you have e raised to q times delta t. This delta t is a consequence of variation in thickness, and this q can be quantified by inputting some values from the Rutherford backscattering. Suppose I have a bright field image and I say, as a consequence of variation in thickness, I have a drop in 5% of the intensity. I can write this as some random number 5 over 100 times q. Suppose this is the maximum intensity. I can fill in from the ideas of scattering cross section that were introduced a few lectures ago on Rutherford backscattering. You can plug in this q in terms of the Avogadro number, the scattering cross section, density of the sample, and the atomic weight. You can also write this in an integral form which appears like this. Suppose I have delta I is the variation in the intensity. This is simply a consequence of the scattering cross section, and let us say along the electron beam column I introduce an aperture and I am recording. So, if here is my specimen and I am recording the intensity values within a region which is scattering from an angle beta like this, or if I do not have any aperture as well, from the small deviation that is caused as a consequence of scattering, say alpha, I can integrate the intensity of the forward scattered electron from this angle alpha to infinity, which is a function of the atomic scattering factor, and this omega is from the differential scattering cross section. We know that there is this, when you have the atomic scattering factor, we have represented the probability of a successful scattering event is d theta over d omega, and this was our expression for the scattering cross section, and from this, instead of theta, it is represented as alpha in this expression, or let me write this as alpha over d omega. You plug in this value in terms of the atomic scattering factor and you integrate it over the complete collection angle, although it is mentioned as infinity here. Depending on the kind of the aperture you are putting in and the range of angles that you are collecting to form an image, you can specifically quantify the intensity from a forward scattered electron beam and the image that is formed as a consequence of the interaction or transmission that has happened in a TEM. So, if I write beta is the angle of collection, it is written in a more explicit way here. The variation in the scattering cross section as a function of beta, you can write it as an integral of this form, where f theta and theta are the angles of scattering and the atomic scattering factor. So, we know that from the Rutherford scattering cross section, the square of atomic scattering cross section gives me the probability of scattering or the differential scattering cross section, and when I put in all these values together, I get some value for intensity. Also, for a specimen with some assumptions in the values of thickness and the wavelength and the atomic number, by using the ideas from Rutherford scattering cross section, I can write f theta as a function of the accelerating voltage. You have the rest mass here. In principle, you can do a relativistic correction as well. The velocity of light, which is written here. So, over here you have this varying when you have relativistic effects considered as well, and then you have the value of the wavelength here, and you have the mass present here or the atomic number, and also the atomic scattering factor as well. So, plugging in all these, you can precisely quantify, and this expression, when all of these are put in here and you simply look at the variation in intensity as a function of scattering angle, this is somewhat proportional to some kind of, let us say if the background is I naught minus, you can write an expression as exponential minus, so times beta. For any forward scattered electrons that are forming a sort of a bright field image, you can always write the intensity variation as a function of some kind of an exponential function, where you have variation in intensity as a function of the background minus the structure factor which is considered within the exponential function. You can actually tune these values and precisely quantify how much of an element is present from which region, provided you know the thickness is uniform within a specimen. These ideas are actually useful in quantifying or even qualitatively getting an idea of what sort of regions are present within the specimen. You can also see that as the intensity variation is dependent on the structure factor or the atomic scattering factor, if I have a grain which is oriented along a specific crystallographic orientation, you call this as orienting the specimen along zone axis, you would see that the path of the electron beam as a consequence of Bragg's diffraction is confined to a very specific path, and the angles of scattering are also well defined. So, this results in what is called as channeling contrast as well. Also, if I have a specimen which is very thin, when I place it in vacuum, it tends to somewhat bend a little, and if I look at the arrangement of atomic planes within a specimen which is bent at a certain angle and which is oriented exactly at a specific angle to the electron beam, let us say I have some variation in the angle with these planes here, if I call this as some theta 1 and this is some theta 2 and so on as theta I, this bending also causes a change in the Bragg diffraction condition for the planes that are arranged internally within this specimen, and this results in what is called as bend contours or diffraction contrast, and we see this primarily in a bright field image. And what you can also do is, once these forward scattered electrons are going along specific paths, I know at which angle they are going to be recorded at the back focal plane, and I can introduce something called as the objective aperture within the back focal plane, and by selecting a specific reflection, I can also record what is called as a dark field image. Let me show you how the most common operating modes in TEM are with help of some example schematic, and by placing the apertures at different positions, you can actually play with the contrast of the image that you are recording. The most common modes in operating in a TEM are, you can have the electron beam incident as a parallel beam illuminating a pretty large area of the specimen, and let us say the beam has some kind of columnar illumination. The interaction region in your specimen is like a small cylindrical disc, and in this, once the electron beam undergoes scattering, it goes under specific angles. Suppose it is scattered at a Bragg angle theta b, I can put in at the back focal plane of the objective lens the objective aperture or the objective diaphragm, and I can select either the central beam alone to form an image. So in this kind of a condition, I have completely, when I do not have any aperture, I simply have a bright background and the variations within the specimen start appearing darker. Or if I now try to obtain image with this kind of a configuration, with an electron beam that is specifically undergone, let us say I call this as theta b1, the first reflection of my interest. The background in this condition, when there is no spot passing through or no diffraction spot which is allowed to pass through the objective aperture, the background would actually be completely dark. That is because, let us say my spots of the electron diffraction pattern are like this, and at this specific location initially, when I do not orient my crystal, there is no spot here. When I configure either by tilting the beam or by moving the aperture, I let this aperture to align with one of these reflections. This set of electron beams which are forming this particular spot pass through the objective aperture, and if you remember, the information here is the Fourier transform of the exit wave that I have here from the object, and from here to the image plane I take another inverse Fourier transform of the Fourier transform of intensity from the specimen. So this results in an image called as a dark field image. So you have a dark background and the features of your interest are forming some kind of a bright feature. We will look at this as an example on how the contrast is varying when I insert a objective aperture. First we will look at how the contrast changes when I insert an objective aperture or when I do not have an objective aperture for a standard bright field image. The images you record in a TEM would appear with a bright background and the variations in the specimen will appear somewhat like this. Here is an example from a silicon crystal on which some gold nanoparticles are dropped, and as you can see, this is placed on a special lacy carbon grid. The background here, what you see which is appearing completely bright, is a complete hole. So here my background intensity, let us say, is I0. As a function of variations in the mass and the thickness in the specimen. So, I know that this is gold and this is silicon. Gold and silicon appear with difference in intensities, and the corresponding diffraction pattern from this particular region appears like this. The specimen is not oriented perfectly into a crystallographic zone axis. I see that the intensities on this side and the intensities on this side are not uniform, but in principle this can be adjusted. However, our purpose is first to see if I place in an aperture around this particular bright spot, how does the contrast in the bright field image I obtain vary. And this is actually called as bright field imaging by using a specific objective aperture. You would typically have in all the microscopes apertures with a diameter of, let us say, 100 micron, 60 micron, 30 micron or 40 micron and so on. And let us see how you can enhance the contrast in a standard bright field image by inserting an aperture. So, if I look at this diffraction pattern, you see that there is an aperture, the shadow or the edge of the aperture is somewhat like this, and it is now allowing only these set of spots to pass through the aperture and form an image at the image plane. So, as a consequence of this, what you are doing is you are not allowing the higher order reflections beyond this point. So, let us say if I call this as reflection G1 and if I call this as 2G1, 2G1 or G1 bar and 2G1 bar are not allowed in this particular condition. When I place the objective aperture and I record a bright field image, you can see that the background and the image or the silicon here is appearing more darker with respect to the background. Likewise, if I change the aperture again and I put in a smaller aperture, so here we put in the 60 micrometer aperture, and in this case we have put in a 30 micrometer aperture. Still the first two reflections are allowed. So, let me call this as the 30 micrometer aperture which is put in. You see that the intensity variation and the features here, the specimen appears significantly more darker here with respect to the background than this particular image here. Before I go further, I would like to draw your attention that in such an image or a bright field image, there are some specific terms. Please do not get confused and mix up. There is something called as intensity, there is something called as brightness, and there is something called as contrast. Like defined in the previous slide, you can say contrast is delta I over I, which is some background intensity. So, variation in the intensity over some background intensity. So, when I say there is brightness, brightness is the flux of electrons coming from the source, which we have seen in our lectures on electron sources. For a fixed brightness, you can still have variations in intensities by inserting apertures, and you start recording variations in intensity here. We call this as darker region and brighter region. Please do not mix up and call this as dark contrast or bright contrast, because contrast itself means difference in intensity. These are a few basic terms. Let us see, as a function of the insertion of the aperture, how the contrast has now changed by drawing a histogram across specific locations. Before I do that, let me just erase all the ink on the slide. So, if I draw or obtain a histogram from the same region on these three images, it is from the same specimen, same orientation, same configuration, only change I have done is insert the aperture. When there is no objective aperture inserted, you can see that the intensity difference is, so the peak intensity at this region right next to the edge of the specimen is somewhat around 200, 210 counts. This is a grayscale image which is displayed from 0 to 255. So here the peak intensity is approximately 200 counts, and the lowest value here is somewhat like 65 counts. So let us say my delta I is 200 minus 65, and in the second configuration, please note that now there is more or less uniformity in the background intensity here as a consequence of inserting an objective aperture. So what this has done is you do not see it directly on the image in a microscope, but when I draw the intensity profiles, the higher order scattered beams are not now allowed to form or contribute to the background intensity as well, and by doing that your background intensity has become more or less uniform. So you can see that this is at somewhat 220 counts, and the median low value is around, let us say, 50 counts. So there is definitely a significant change in the contrast value. From 220 minus 50 is approximately a range of 170 counts, whereas this is around 140 counts. In the third condition, with an even smaller aperture, I have not allowed even these reflections to pass through in this situation, and there is a slightly more variation in the intensities within the specimen and outside the specimen, and there is more enhancement in contrast. If I actually see, I do not see significant improvement in contrast between these two. So although there are no significant variations in the contrast that is obtained between these two images, you can see that there is still some subtle variations in the information I get from the features here. Most importantly, I can see that the bend contours, or the consequence of diffraction contrast close to this edge of this specimen, is more prominent here in comparison with here, and I hardly see these features in this configuration. So by selectively choosing which set of electron beams following which specific path are contributing to forming an image, you can get specific information from the specimen. And with this, you can identify different kinds of defects, you can identify specific phases, you can do a whole lot of different kinds of imaging in conventional TEM. So if I summarize this, what we've actually seen here is when an incident electron beam with more or less uniform intensity is incident on a specimen, you are obtaining images with varying intensity, and this intensity can specifically be quantified in terms of the structure factor or the atomic scattering factor from the Rutherford scattering experiment, or the Rutherford expression for particle scattering, and you can obtain either diffraction patterns or you can form images from the forward scattered beam. The beams that are contributing to form a diffraction pattern appear as spots on the backfocal plane, and these positions of the spots have specific locations which can be related with the internal arrangement of atoms within the specimen, and that is what is being done in diffraction. There are different kinds of diffraction studies that can be done by tuning the incident beam as well. We'll go into those details at a later stage, but specifically when there are specific defects like dislocations, or let us say some specific grains with a specific orientation, you can index these diffraction patterns and identify which is the reflection of your interest, and by centering an aperture around those particular reflections of your interest, you can form bright field, weak beam dark field images and get meaningful analysis from the specimen. As an example, I'll show you a comparison between bright field and dark field images from the same specimen. Here is an aluminum sample which has some copper precipitates on top. we were interested to see some kind of dislocations that are present in this particular region close to a grain boundary. So, by specifically choosing one set of reflections, there is something called as the two-beam condition. We will look at it slightly later after we understand how diffraction patterns are obtained. But for now, from the diffraction patterns that are obtained from this kind of a specimen, by specifically tuning the aperture to allow only a specific set of reflections, I can form this kind of an image. So, here my background is bright and my features of interest are dark, whereas here my background is dark and the features of interest appear brighter. So, that is how you can obtain different images with varying intensities, and these are all examples of what is called as amplitude contrast in a transmission electron microscope. Let us now see what are some basic steps you need to take before you go to a demonstration session on the microscope. After explaining what is done in the experimental hands-on session, we will end this lecture. If you look at the microscope column again, the intention to do the alignments within a microscope when you load a specimen is you start by looking at how the source is. So, if I look at the ray diagram, I will start by tuning the condenser lens currents, and I can tune the condenser stigmatism, and then I have to first bring the specimen to the right height. As you know that the lenses here are electromagnetic lenses, and you have to bring the specimen to the right height coinciding with the location where my magnetic field is more or less uniform in between the split pole piece. You call this as bringing it to the eucentric height. In other words, what happens is when I insert a specimen holder like this, the holder configuration is somewhat like this, and let us say if this is the axis of the holder, if I tilt the specimen along the axis of the holder, in this geol microscope you call this as X tilt, in Thermo Fisher you call this as the alpha tilt, you can call it as primary or secondary tilts. When I am tilting the specimen holder, the feature of interest on my specimen should not move away as a consequence of the tilt, and you are continuously obtaining projected images. To let this minimize, you would like to let the axis of the holder coincide with the optic axis of the microscope. So, when the holder comes in, I want this axis to coincide with this axis, and this adjustment is called as eucentric height correction. Once you do the eucentric height correction and you identify the features of your interest, you start obtaining the images. So, let us now end this lecture here, and we will move on to a demonstration session where we will start by seeing how to load a holder in the lanthanum hexaboride filament TEM, and then we will also see the examples from the cold fig TEM, and we will look at some demonstration sessions on obtaining a basic set of images. After these images are obtained, we will start analyzing the data that we get, and we will correlate it with the intensity variations like we saw on the previous slide. Thank you.